Okay, well, if the subject line didn't throw you and make you wonder, number one, this doesn't have anything to do with calculators, but I hope the topic is of interest to you and might wake you up a little bit. So jumping jack flash. Okay, it's a gas. That's what I'm talking about. I'm talking about a home loudspeaker for home listening, audio listening, music listening, that doesn't have conventional cones and tweeters and this sort of thing. It generates sound basically from mid-range on up through what's called a plasma driver, which basically it uses helium to generate the sound. Okay? This guy, Alan Hill, was a rather interesting individual. Started as a toddler sticking his fingers or whatever into electrical outlets and said, oh, gee, that's fun, let me try it again. He heard a little, he cried, he went back and he did it again. So he's a precocious little guy and started studying science and everything else, and he loved all sorts of things. He became a ham operator. He learned Morse code. In high school, he was the first person in San Diego to receive signal from Sputnik. And so as a result, and that he was written up in the newspapers as a result. And his classmates took amusement at that and decided that when he walked by them in the hallway, they would go beep, beep, beep. And so that was fun. He went to a science fair and he won second prize as his high school senior project. University of Michigan sponsored a big field trip for people who were National Science Fair winners, and he went. And one thing he particularly liked at that school was the cyclotron, so he decided he wanted to attend. During his third year at the University of Michigan, he also showed his faculty member by the name of Peter, I can't read his name, a magnetically crushed aluminum pipe from his senior science fair experiment, asking him, how do you think that got that way? Peter had no idea, but invited Alan to work there at the school for the summertime. So instead of going back to San Diego, he stayed there. He went on to get his master's degree there, and at his summer job after getting the master's at Lear-Siegler, his biggest challenge was to increase laser power for practical uses with a CO2 laser. And he turned out to be very successful. This is him, and you'll see this thing at the bottom going across. It's a 6-inch diameter high-powered laser. Anyway, the government, the Air Force Weapons Lab happened to hear about this. They had started their airborne laser project at Kirtland Air Force Base in Albuquerque, and they heard about Alan's work and at Lear-Siegler and offered Lear-Siegler $1 million for him and his laser, which was pretty remarkable. Peter, his faculty advisor, advised him, you better forget your PhD that he was going to go for and take the job at Kirtland because what you're doing is far too important, far too groundbreaking to pass up. So that's what he did. I'll reference some in my paper in the directory, and I'll get to this in a moment. There's a link in the proceedings, there's my paper, which after the first paragraph lists pertinent files, and that points to a Google Drive folder that I have, which you can refer to, and it has a whole bunch of interesting stuff. This is actually the plasma driver in the loudspeaker, okay? And I'll explain what that's all about. So he developed this thing while he was busy working, and came up with a way to develop. He in his laser work, he determined that airflow was causing the laser to deflect or something like that. During his experimentation, he said, "Oh, maybe I can do the reverse. Maybe I can cause high energy to deflect the helium." And so, in any event, that's what he did, and that's what gave launch to Hill Plasmatronics, the company that he founded after he left them. And he started this idea of creating a speaker using helium ultimately. And there was a company called Duquesne Company, this is back in the 60s, who had developed a product called the Ionovac tweeter. Some people may have heard of that. That was outrageously expensive back then. Ultimately, was later made by a company called Electro Voice. Some of you have probably heard of that company. And that was phased out in 1963. That, however, was thought as an incredible tweeter. It went from 2 kilohertz to 40 kilohertz. And so, in any event, he proceeded to develop the plasma driver, and by controlling the shape of the plasma of ionized gas, he found that he was able to control the lasing. By shaping it, he was able to, that was key to high efficiency and making a wider frequency range, and having a larger plasma field. I want to play this video which explains how this thing works.
So, what's the best speaker ever made? Could it be a time-aligned multi-box cone system worth over $250,000? Or how about a full-range electrostat dipole with the thinnest possible membrane? Or maybe a horn system that can faithfully reproduce the dynamics of live audio? All great answers, unless you've heard the Hill Type 1 plasma speaker from Plasmatronics. A speaker with technology that lends itself to the most spectacular measurements. It was accurately compared to an SR-71 Blackbird lurking in a field of Boeing 737s at the time. So Alan Hill was working on his PhD at the University of Michigan on lasers, and he happened to discover what was keeping CO2 lasers at the time from putting out more than a few hundred watts. And he knew it could put out tens of kilowatts, and the government seized his notes and classified them. His advisor said, "Forget your PhD, go to work for the Air Force Weapons Lab in Albuquerque," which he did. So while he was there, he was working on plasmas, big volume plasmas for lasers, and he realized that acoustic waves were modulating the plasma, and he also realized the opposite could be done, and that's where this comes in. It took him about 10 years all told to get it to market. So that would be about 1967 or 8 where he started, and he came out with these in 1978. So why do I have these things? Well, I used to work for Alan Hill back in the 70s and 80s, and he came out with these in 1978 at the first WCES. So let's talk about some of the myths about these speakers. Let's see. Ozone. No ozone. They're too hot. They don't make ozone. Corona discharges that are cold make ozone. These are not corona discharges. They're glow discharge. which is a very hot plasma. And how does it make sound? Well, it's doing that by modulating the temperature of a sheath, a very steep gradient of temperature from the plasma to room temperature. It's like a millimeter thick or less. When the power is modulated, that moves, that area moves, and that launches acoustic waves. Not ions, not electric fields doing it, heat. Let's see. UV. Well, they make a little UV, not that much. I stare at them all the time, I'm fine. Why do they have to run on helium? Good question. Well, helium has two properties I know of. I am not an expert. Alan Hill, the physicist who developed these, knows all the reasons. But two of them are the ionization energy is high. So the voltage drop across here is high. The power, therefore, is high. Argon would be much lower. Second is the thermal properties of helium are extraordinarily good for doing this with low distortion. Turn down the helium, more air in there, distortion goes up. So yeah, helium's needed. You will have a once-in-a-lifetime chance to hear these tweeters at Axpona. They will be paired with an LFT 8B set of speakers from Eminent Technology. Sadly, I do not own a pair, but they will be there. They're down in Chicago waiting for these things. So Alan and his family live in New Mexico still, and although he's getting old, I might be able to convince him to come to this thing. It all depends on what kind of reception we get. So, crossing my fingers. Nothing I can show you here on this recording will do justice to these things. It sounds like crap on the YouTube. You won't like it. You got to come in. You got to hear them live to understand what these do. So please come in.
Jet trail in the sunset a long way away, cutting across the horizon at the edge of the day, and it calls out to me, come fly away.
There were 3 sailors, bold and true, with cargo they did carry.
Okay.
So,
Yes.
if I understand, he's supplying gaseous hydrogen to.
The speaker, each loudspeaker has a full-size cylinder of helium in it. And I'll show you pictures of everything.
Hey, Brian,
Yes.
is that plasma we were seeing happening in the open at atmospheric pressure? Or?
It is. And it's 0.5 millimeter thick. In the center where all the heat is, so you see the purple, there's 5 cathodes at the bottom where helium bleeds in. At the top is an anode, and there's an amplifier section on each of the 5 cathodes at the bottom, high voltage, and then in the middle is where the helium and the air mix together, and that's the yellowish color.
What kind of consumption of helium are we talking about?
A full cylinder of helium at roughly 2,000 psi lasts for about 300 hours of playing time. Okay? Helium, the cost of helium has gone up dramatically in the last 20, 30 years. And a lot of it comes from the panhandle of Texas for some funny reason. In any event, the center of that flame, if you will, is at about 36,000 degrees Fahrenheit. So you have within a quarter millimeter, you have an extremely steep temperature gradient from 36,000 down to room temperature. And by by adjusting the current back and forth, that's what creates the modulation of the sound. These will play, 90 dB at 10 feet in an average size room, 1% total harmonic distortion. You see, you have a massless diaphragm, and these things are driven directly by the outputs of the tube amps, which are built in, okay? So you have no transformers, no nothing. You have no electromechanical device in the middle, okay? The frequency response of these things, they crossed over either at 700 hertz or 1,000 hertz, or if you have some different crossover, in any event, they go on up to ultrasonic. The upper limit is about 180 kilohertz, which is pretty far above human hearing. This talks about, here you're talking about all the differences, or what, the rapid change in plasma power is too fast for heat transfer, thus the air density change, and that's what launches the acoustic wave. It creates essentially a pulsating sphere, okay, the ideal pulsating sphere to create sound. It doesn't have out of phase information. It's so basically you have instantaneous impulse response. There's no loss. So that's basically it. You talk about the human hearing. Yes, a very young person might be able to hear 20 kilohertz. But the thing is, the timing differences between what our ears hear enables us to locate sounds. And so you can, your hearing you may not hear that in a hearing test, but you can locate sounds much better. Okay? This is Alan in his lab developing the loudspeaker. Okay? This is a picture of the speakers with and without the grills. That's the plasma driver glowing purple in the middle up top, and that's the control panel, and I'll show you that in a moment. Yes, sir.
So then this is primarily for the higher range, because you still see woofers here.
From, the 6.5 inch woofer and 14 inch woofer and 6.5 mid-range, serving from typically 1 kilohertz downward, okay? So everything above that there's no crossover in the plasma.
That makes sense.
Yes. And so I'll cover all that. This is the whole plasma section. That's the controls up top. The 5 little things here in the middle are for controlling the current. This is for controlling the helium flow. This is for meters to show the current. And then there's different things.
Show them,
The current.
6 arcs.
There's 5 cathodes, and then the anode at the top.
Okay, that's what
Okay? So those are for the cathodes. This is taken from a book which Alan used sort of as his absolute reference, a book titled, and it's referenced in my paper, about gaseous conductors and, sorry?
Cobine?
Yes, I believe so. And it's referred to, there's a link that you can actually download that whole book, or at least view it online. And it's quite informative. It shows this discharge curve for glow discharge. You see there's differences. There's 2 kinds of discharge. And that fellow that did the video, that's Tony Salsic, who worked for Alan for 12 and a half years. He talks about glow discharge. Those are typically cold temperature, and they generate ozone, okay? And they also generate a fair amount of ultraviolet, okay? A glow discharge is super high temperature, as I said, approximately 36,000 degrees Fahrenheit. Doesn't generate ozone because it burns off. And generates a little bit of ultraviolet, but not a lot. So in typically the point B is where you're operating. That horizontal line to the left of it is why variation in voltage doesn't change. Current goes horizontal. So B is typically the operating point where you're running. This is a picture of one of the pair of plasmatronics that I bought a few months ago from a former dealer up in Minneapolis, sitting around for 40 years in storage, so that's why all the dust. But they're in mint condition. So this is the back, and in the back is the space for the helium tank to go. You see the tube amp inside the cage with big tall resistors inside, the oil-filled caps up top, the big monsters, and then the big power cord and everything else for it. This shows one of the plasma modules, obviously covered with dust, sitting in a box that's looking down on the top. This is the front of one of the helium modules without that grill across, and you'll see that this is the plasma driver. This is the tubing coming in from the helium, and then these are the power from the amplifier. Okay, and then you see the control panels above that.
Are those fire bricks there in front of them?
Say again?
Are those fire bricks
Looks
to
like
either
foam.
side?
No, these are foam, and that's to prevent acoustic reflection off the front grille. So that's the whole idea.
What did a set of these cost back then?
Interesting, good question. They came out in '78, made until '83, and when they first came out, there were about 6,500 or 7,000, which is insane money. At the end, they were up to 10,000 a pair. This is just showing a close-up of the control panel. And mine are serial number 54, which is one of the very last pair made. This is showing the cleaned up module, different views. That's the left-hand side. You can see the tubing going into the helium. That's the right-hand side, showing an amplifier with the tubes.
What kind of tubes do they use?
Excuse me?
What kind of tubes did those use?
6MJ6 or 6JE6, and which are not made anymore because they were used for flyback circuits and tube-type color TVs. So they can be found, but you have to look. This is the external crossover unit, so you have a choice of crossing over either 700 hertz or 1,000 hertz, and then just adjusting it. At clipping, it crossed over at 1,000 hertz. Clipping generally max output is about 170 dB, so they'll play very loud. And that's the back showing the connections. It's pretty darn loud.
Are you going to spring for some helium and try them?
My speakers are almost ready to go, so
Should be able to hear them.
the plasma modules will be. We won't hear them here, but they're pretty loud. This is a completely different topic, but related to demonstrate why sound from musical instruments goes well above 20K. This happens to be a trumpet, and you'll see that if you, and this paper, which was written by a Caltech professor of music, James Boyk, who is a classical pianist, shows the frequency spectra of, for example, a trumpet, but you'll also see that stringed instruments and especially drums generate tons and tons of very high frequencies. So frequencies up to above 100K, and you hear that. So that's why why the gray-haired ladies go into the concerts go because they can appreciate the sound, even though their hearing only cuts off at probably 5K. In any event, I think that's it. A couple of guys, Tony on the left, Alan Hill's son, Larry on the right, happened to be wearing the same shirt as me. But that was at Alan's memorial in early August. He had passed away on Memorial Day, unfortunately. He was 83. Other questions?
What generates the striking arc?
Sorry?
what generates the striking arc. In a normal plasma torch, it's either a contact that's open when the gas pressure's turned on. It generates a small arc which starts the
Yeah,
plasma stream.
unfortunately, I'm not up on that yet. Yeah. So, that's it.
Thank you.